Hi. So for question 4a, we've been told that y equals e to the power of 2x tan x, and x does not equal any odd number multiples of pi over 2. We've been asked to show that the turning points occur when tan x equals -1. Okay, so the first thing we're going to do is we're going to differentiate this function with respect to x, okay? So that we can find the gradient function. Now, you should know that this function consists of two terms multiplied together, okay, and this cannot be simplified. So in order to differentiate this function, we're going to be using the product rule, and I have it here, Q layer 1. When a function y comes in the form uv, the differential of this function, y dash, is equal to u times by the differential of v plus v times by the differential of u. Okay? So in order to find y dash, which simply means dy by dx, we take the first term and multiply it by the derivative of the second term. Okay, so it's going to be e to the power of 2x multiplied by the derivative of tan x. Now you should know that as a standard derivative, that's sec squared x. And this is plus the derivative of e to the power of 2x. Now, in order to find that, we're going to have to use a chain rule because this is a function within a function. Okay? So off to the side here, what we're going to do in order to find dy by dx of this function, we're going to find dy by du. We're going to make a substitution u and find dy by du, and multiply this by du by dx, and it's as if the du's will cancel out. So we'll see here. We're going to let y equal e to the power of u, where u equals 2x. So dy by du is equal to e to the power of u, because we know that e differentiates to e, and du by dx, you should know, differentiates simply to 2. Okay, so dy by dx is simply dy by du multiplied by du by dx. Okay, so e to the power of u multiplied by 2. So it's 2e to the power of u. And we know what u is. U is simply 2x. So we can replace this with 2x to get our derivative in terms of x. Okay, so now we can substitute this in back into our formula. So we know that e to the power of 2x differentiates to 2e to the power of 2x. And we're going to multiply this by tan x. Okay? Okay, so in order to find the turning points, we're going to have to equate our derivative to 0, because we know the turning points occur when dy by dx is equal to 0. The turning points occur when the gradient is equal to 0, okay? So we're going to have to equate our gradient function to 0, okay? And before I do that, I'm going to factorize out. So I'm going to do that, and I'm going to factorize out an e to the power of 2x on the next line. Okay, so I'm just going to factorize out e to the power of 2x. So I'm left with sec squared x plus 2 tan x. Okay? And we know that this is equal to 0. Okay, so there's going to be two solutions here. We're going to equate the e to the power of 2x to 0, and we're also going to equate this bracket to 0 as well. Okay, so e to the power of 2x equals 0. What I can do here in order to solve for x is I can take the natural log of both sides. Okay, So the natural log of e to the power of 2x is simply 2x, and the natural log of 0 is 1. Dividing both sides by 2, you get your first solution, which is x equals a half. Now that doesn't look like anything that's been given in the question, so hopefully the answer will pop out here. And it looks like it will, because we have tans and trig functions here, and there's a tan here as well, okay? So sec squared x plus 2 tan x is equal to 0. Okay, so we're seeing sec squared and we're seeing tan, so you should be thinking of a certain trig identity now, q layer 2. So we know that tan squared x plus 1 is identical to sec squared x, okay? And this can be derived from the well-known identity sine squared x plus cos squared x is identical to 1. Okay, so if you divide all the terms in that identity by cos squared x, you can derive this identity. Okay, so it's a handy way so you don't have to memorize it all the time. So we can name this equation 1, and we can substitute equation 1 into here. Okay, identity 1. So sec squared x is identical to tan squared x plus 1, and we still have plus 2 tan x is equal to 0. Okay, so I'm going to make a little substitution here to make things easier. I'm going to say let a equal tan x, so we therefore have a squared plus 1 plus 2a is equal to 0. Now I can just rearrange this, and you should be aware of the fact that this is a quadratic equation now. Okay, so I can factorize this quadratic equation, and it factorizes quite easily. It's simply a plus 1. A plus 1. Okay, so a is equal to minus 1, and because a is tan x, we can therefore say that tan x is equal to minus 1, just like in the question.